Alright, welcome to the Supernetting video in the Isaac's Dev Corner networking series. We're going to get straight into it. The last video was the subnetting video. So this is the Supernetting video, which is basically the opposite of subnetting. So instead of taking bits from the host portion, you're taking bits from the network portion. And you're sort of aggregating networks. But we'll look into the descriptions and all that in a second. So let's go. Okay, let's move on to the next slide. So, also known as network summarization, Supernetting combines a group of continuous networks, or subnets, sorry, to form a single network. Used for route aggregation to reduce the size of routing tables. Consolidate continuous routes into a single route for route advertisement. So, the primary sort of purpose of Supernetting is to reduce the size of the routing table in a network, making it more efficient and easier to manage. So it's just basically making the routing table more efficient. And we'll go into routing in the next video, and we can sort of understand why it makes sense. But essentially, as it says, you're summarizing a bunch of networks or subnets, and you're aggregating them to reduce the routing table size. So, for example, we've got the network, this one, so 193.2.1.0/24 network. So this is how it's seen externally, but this network may be a subnet, so two subnets. We've got obviously with the 24 CIDR notation network, you've got 256 potential hosts. That's including network and broadcast from each side. So if you look at this, if it was into two subnets, we would have 128 as our next subnet, which would follow on. So you can see here we've got 0, then 128 is your second subnet in terms of where they start in the IP address. So what has been done here is you've sort of aggregated them and you've supernetted them. So what you've basically done here is you've taken a bit back and you've then aggregated them, meaning that it goes back into the original sort of format. Not the original format, but it depends how many times you supernet to. But for this example, you went to /24, meaning this is where you're going to be sitting. You got the last octet for the host portion. So that puts you at 256 potential here, which is obviously a full network. So that's going to be your route that's what's going to be visible on the router. So as it's seen here, the network is seen as this as a whole network externally, rather than these ones that are going to be seen in subdivisions, I guess, what you could say. Okay? We'll go into how it's done, but give us a second. We've got this example too, which is a 193.2.1.0/24, and this has been split up into a /26, which means there's 2 bits on the host portion, meaning you've then subnetted by 2 to the power of n, which is 4. So you have 4 subnets, each starting at increments of so you've borrowed 2 bits, meaning you would have 2 to the power of 6. 2 to the power of 6, I'm pretty sure, is 64 increments per subnet, which would be here 0, 64, 128, 192, and the next one, like that would extend to whatever it would. So yeah, aggregation of these networks would equal that. We'll get into how it's done, but you can get the main premise here. You're sort of getting the base network of what all these would be. Okay, now this is to make the routing table more efficient. So we'll go into the next slide. So opposite to subnetting, borrow bits from the network portion. You borrow bits from the network portion. Combine group of continuous networks and addresses to form a single larger network. Manipulate subnet supernet mask to form a supernet. Key lies in supernet mask. Mask distinguishes network bits from host bits. When mask is applied to any address in any of the network addresses, making up the supernet, resultant network address is the same as the first network. We'll get into why it's that. So if you go back to the slide here, it's always going to be the first subnet is going to be the one that's represented as the network externally to the routers, okay, rather than like this one, for example, in the subnet when you aggregate them together. And the reason because of that is because of the subnet the Supernet mask. Which is what we'll use to like sort of distinguish what's going on and how to do that. But we'll get in that in a second. Routers need only know one address for an entire Supernet. Reduces load on internet routers, so it's just making things more efficient. Yeah, so subnetting involves borrowing network bits from the left of the default mask boundary. Subnetting involves borrowing host bits, so it's the opposite. Okay, so the reason it's 255.255.248.0 for the supernetted mask is because that's what's required to aggregate 8 networks as seen visibly here. Now, I just did a bit of the arithmetic before, and in terms of what it looks like, in the third octet is 1 1 1 1 1 0 0 0. So 5 ones, 3 zeros in the third octet, which is going to be 3 bits on the network portion, which have been taken backwards. So that's going to aggregate a total of 2 to the power 3, which is 8 networks, which fits this perfectly. And when you layer that onto the, when you do a check to make sure you can see that, because you need to make sure that your 168 address is going to be your network address visible, because when you aggregate, you're just getting one network that's going to be visible, and that's going to be the first network on the subnet, which you can see here. Now, the way you can do that is you can do a match setup. So I'll try and draw this, if I can draw this for a second. It's going to draw. Nope. Okay. We'll go back. Maybe pen here. Okay, so for example, you have, I did it before, but if you look here, right? So let's say we pick so the subnet mask is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then you've got your 0. Well, 1, 2, 3, 4, 5, blah, blah, etc. Right? We already know that that's going to be 0, so don't worry about that. Now, the way you can check to make sure that the network address is going to be the first one, which is up here, is if you sub in your value. So maybe let's just sub in the last one to check. So we know that that's going to be, we don't need to worry about this one. We're just going to worry about the third octet because that's what matters, because they're all different, as you can see here. So what we're going to do is we're going to plug that in here. So 168 is visible as this. Oh no, 175, sorry. Is going to be 0, 0, 1, 0, 1, 1, 1, 1. Now this would convert if you do the binary conversion, which you can look up on how it works, but if it's basically 1, 1, it equals 1. If it's 0, 1, it equals 0. 1, 1 equals 1. 0, 0, 1, 0, 0, 0. And that is going to equal 128 plus 32 plus 8. Now, if you do the maths there real quick, 128 plus 32 plus 8 is 168. 168, which is the value of that network up there. So that's going to aggregate that properly. And then that's your subnet mask, because we figured out you're going to have to borrow 8 bits from the network portion to aggregate 8 networks. And then your network portion, your next hop is going to be exactly the same as before, because they all have the same next hop. And that's the reason we're aggregating them in that way. Okay? So that should make sense. If you need more clarification, we'll go over that in the next examples that we're going to do. Anyway, next slide. So, on this slide here, we can see we have the network 193.0.0.0/22. /22 is going to be 4 networks, as you can see here. So this is our ISP, which is going to be the internet provider. So the internet provider right here, or as you can see right here, is, giving internet to all these different networks, whatever. But you can see that I can access these different networks over here. So you've obviously got 1, 2, 3, 4, 5 networks, and you've got this network right here too, which is going to be getting the next hop directly. But so this one is directly connected, which means the next hop is straight away there. But these different networks, to access these different networks up here, so not this one here, but these ones over here. So here, 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 and here, you will have to aggregate them to make them more efficient in the routing table. So /22 becomes /24 subsequently because you're borrowing 2 bits from the network portion, which is 2 to the power of 2, which is going to be 4. They all have the same next direct hop, which is over here. So if you aggregate them, you will get the subnet mask of 22. And we can also apply that rule that we tried before. And you can do that right now, actually, if you want to pause the video and you can check. Let's just plug in that one, for example. And its network address with the subnet mask of /22. If you do the binary conversion, which I did before, like that stuff, and then you go like 0, 1, 0, whatever, right? Blah, blah, blah. It should equal this. So you should end up getting 192.0.0.0/20. Well, don't worry about the slash thing yet, but that's the network you should get, which is going to be this network right over here, as you can see. So it means you only need to have 2 routing table entries for these networks right here. This network is a different network. It's not part of the subnet, which has been set up here. So as you can see here, that is one way you could do it. So yeah, hope that makes sense. Next slide. So why does the common resultant network address become blah, blah, blah? So you identify the common bits. As you can see, the common bits are yeah, so that's 192, that's 0, and the next one is going to be 0. So if you look here, they're all going to be that. So what you can basically do to decipher what it's going to be is sort of cut this up here, over here, and you can basically just see that where it's unchanged, that's what you're going to have. So this is going to be your network. So this bit here is going to be what's visible. Does that make sense? So here, now that is going to represent that. So to create a subnet, we take the common bits and extend the subnet mask over to cover all 4 networks. The notation /22 indicates the first 22 bits are part of the network portion. First 22 bits are subsequently these bits right here. So remove that because it's obviously 8, 8, 8, 8. So it's going to be 16 for the first 2. Now then 16 plus 6 equals 24, or 22, sorry. And yeah, 22 is that. And that's going to be represented as this network over here. Okay? So benefits of supernetting: to minimize latency in complex network structure, to reduce overhead for routing processes, since the reduced number of route entries in the routing table, to improve network stability by reducing or eliminating unnecessary routing updates after part of the network undergoes a change in topology, to reduce process and workloads, memory requirements, and bandwidth. Common sense stuff there, as we've discussed. So we borrow bits from the network portion, as we discussed, manipulate the network mask to form a supernet, which is the stuff we were doing to decide how many bits we're going to need, and then what that's going to look like in our subnet mask. Okay, so the key lies in network mask, which is the mask distinguish network bits from the host portion. When the mask is applied to any network, you will get the network address as the resultant, doing that little binary math thing, which I showed you before. If you plug in and you just push them all together, you'll be able to see that they will all aggregate to the first network address, which is going to be the one that's going to be represented on the router. So even if you have 32 networks, the first network that starts that subnet is going to be the one that's visible, and it's going to be, but obviously going to be supernetted in a way. Okay. So identify the number of networks in the aggregate, determine the number of bits borrowed to form a network portion, define the mask. Okay, let's take this example. So assume a mid-size organization. Class requires 1,000 addresses. How many Class C addresses are required? So, well, this one's a bit of a trick question, but in 1,000 addresses, obviously Class C network is going to be the third octet, right? It's going to look like this. It's going to be 1, 1, 1, 1, 1 for Class C. 1, 2, 3, 4, 5, 6, 7, 8, which is equal to 255. Which means your last octet is going to be 0, 0, 0, 0, 0, 0, 0, 0, which is going to be equal to, a potential of, in terms of hosts, you have 256. Like including broadcast and network, but like, whatever. That obviously does not fit that requirement. So we're obviously going to have to split this up into 4 networks to equal this, because that's just not going to work. So 256 times 4 is how many networks is what we're going to need. We're going to need 4 class C addresses required for this network. Okay, and the subnet mask. Well, the subnet mask is going to be the aggregation of these networks, and what that's good. Let's see what that's going to look like. All right. So the 1,000 addresses would normally require a class B network, obviously. Now we've done that in our previous videos where we went through that. Instead, a range of 4 class C addresses is allocated and Supernet to the organization. It can be reached through a single network address. Each class C address has 254 host addresses, so that's valid host addresses that actually aren't broadcast and network. Now, 4 networks are required. So we're going to have to borrow 4 bits on the network portion. So 4 bits network portion. My spelling's terrible, but that's going to look like this. Sorry, not 4 bits, 2 bits to form 4 network. And that's going to look like this. So these bits have been borrowed, meaning your subnet mask is subsequently this right here. Okay? So that should make sense there. And then that's going to be the subnet mask for, the 4 class C networks. We don't know the addresses for them yet, but that's okay. I guess the addresses have been given to us right now. Suppose the 4 addresses are allocated, our organizations are here. Now, as you can see here, these are the bits that have been borrowed, meaning the first network address, the one that's going to be visible on the router, is going to be this right here. So this portion right here. So that's going to be 8 out of 4. Oh, wait, no, hold on. 1, 2, 8, 64, 32, 16, 8, 4. So it's going to be this one right here. That's going to be the first network. Well, it's going to be what's visible to the router. Applying the mask of 252, which is right here, to this section here, any of these networks resolve to this right here, which is going to be the first one up there I've established. The bits borrowed for the Supernet are masked off with the host bits leaving the ID of the network only. Okay? So, yeah, that makes sense. So this bit is going to be reserved for the subnet section, or the Supernet section. And this is, yeah. And you've aggregated them using just this bit portion here, which is not part of which is the section that they're all the same on each network. Does that make sense? And here's the checker, and here's the chart if you want to use this and print this down. But for example, they picked number 6, which is going to be this network right over here. And then we're going to check if it equals 4, which is going to be the first network address right over here. Okay. So the binary is right here. Supernet mask is right here. And that should be, Supernet mask is obviously 52. Yep, you do the math, it equals that equals that, and then you cut it off here. So right here is where you'll stop that. Oh wait, no, never mind, not there. That's wrong. But this section right here, so it'll only be 4, because it's 4, 2, 1, 8, 16, 32, 64, 1, 2, 8. So 4 is your visible section here, then nothing else there. Okay. So CIDR classes into domain routing. Addressing by class has been superseded by a more flexible addressing method. Classless interdomain routing, CIDR. The network and host demarcation, interesting word, can be made with any number of bits from beginning of address. Example, a class C address network section is 42, 22, 24 bits. Using CIDR, an address registry can assign an address with a network section of 26 bits. So if you look here, you've got /26, which is going to be 4 subnets right here, and I sort of aggregate that into just this first one over here, as you can see here, using the side notation there. Subnetting divides networks into 2 or more subnetworks addresses with fewer host ID bits for each. Okay. Let's take this example, which was an interesting one. Instead of applying 2 Class C addresses, a company could contact a ISP, which would lease 500 IP addresses to the company. The addresses are not identified by any class. They're simply contiguous block of IP addresses. So this 23 network is equal to /24/24, and you need 500 addresses. So this is your next subnet right here. Now the reason that is because the first one is going to be 255. It's going to go from 0 to 255, and then the next one is going to go from 0 to 255 in the sense, but you have to flick this bit, which has been the last bit in the third octet, to on to represent the next network, and that's going to have a capability of 20255, which is going to equal to the 500 potential with the two subnets, and then you can aggregate that using the /23, which is going to equal this right over here. So classless addressing has led to much more efficient allocation of IP addresses in the address space. Now, subnetting versus supernetting. The process of dividing a network into groups of smaller networks. That's dividing. This is the subnetting one. To enable reduction and management of broadcast domains, host bits are borrowed to be used as subnet. Manipulate the subnet mask to divide a network into subnets. The process of combining, this is supernetting, combining a group of continuous network addresses to form a single network, to reduce the number of entries in a routing table, to simplify the routing processes. Network bits are borrowed to be used as the host ID bit. Manipulate the network mask to form a supernet. Okay, that should all make sense. Next video, we're going to cover routing. Now, this is going to be an interesting topic. It's very in-depth too. But yeah, let's look forward to it and catch you guys in the next one.